Let us take a look at what is going on in C. And actually, we're back to drawing payment streams again. Here it says, assume the person receives 1 unit of money when he dies. So, when does the person die? Well, we let n be the remaining lifetime of a person. So if we stand at time 0 now, then the person dies at time n. So he receives 1 unit of money when he dies. So this is 1. What is the expected present value of his benefit? So this 1 unit of money, its present value now, well, we take it and discount it capital N periods. We don't know what this capital N is, but if we know it, then we know that it should be discounted in periods. So the present value of his payout is V to the capital N. And since the capital N is stochastic, we don't talk about present value, but instead we talk about expected present value. So what we want to do in part C is find the expected present value. We want to find the expected value of V to the nth, and that would then be the price that the person should pay to receive an insurance contract where his family receives 1 unit the time he dies. Let's just also take a look at D to see how D differs from C. So in D, we assume the person receives 1 unit every year as long as he is alive, starting from next year. So at time 0, he gets nothing, but at time 1, he gets 1, 1 at time 2, and 1 at time 3, and so on, as long as he is alive. So he keeps receiving money until he dies at time n, and then afterwards, he receives no more money. What is the expected present value of this benefit then? Well, we can see that this payment has expected present value V to the first. This payment has expected present value V to the second, and so on until the last payment, which is discounted in periods backwards, so it has expected value V to the nth. Now this is equal to the sum for k equals to 1 all the way up to n of V to the k. So what we want to find here, when we want to find the expected present value, is we take the expectation of the sum for k going from 1 to n V to the k. And you should all kind of look at this and think, well, I know something about that. It kind of looks like a geometric sum. So just keep that in mind. Let's start with C, where we want to find the mean of V to the n. Let's just take the good old-fashioned expectation definition, which is given as we want to take the sum for all values of n going from 0 to infinity of V to the n multiplied by the probability of n attaining that value. And let us plug in the point probabilities now. So the point probability is given by p multiplied by 1 minus p to the nth. So what can I do? I can take p outside of the summation, and then inside the summation, I have n equals 0 to infinity of v times 1 minus p to the nth. And what does this give me then? Well, I recall that the geometric series formula tells me that this is equal to 1 over 1 minus whatever I have in here that's lifted up to a power. So I know that this expression that I have is equal to 1 over v multiplied by 1 minus p. So I just note here that v multiplied by 1 minus p does in fact lie between 0 and 1. Since the discount factor is between 0 and 1, because this is equal to 1 divided by something that is greater than 1, we assume anyways, and this is also somewhere between 0 and 1. Okay, so this is equal to P divided by v multiplied by 1 minus p. So that is the expected present value of, oh sorry, I think I forgot the 1 minus, right? There is a 1 minus here, so 1 minus, then 1 minus, that's right. So that is the expected present value of the contract in C, which is some kind of term insurance almost. Okay, so let us try to find the expected present value of the contract in D. In D, we want to find the mean value of the sum going from 1 up to n of v to the k. And we can do this in different ways, but since the geometric sum formula we have here goes from 0 to n minus 1, let us just use whatever we have at hand and just change this formula over here by saying, well, let us take a v outside of the sum, because then inside of the sum, what we have left is v to the k minus 1, right? And then I can shift the k minus 1. I can shift the minus 1 into the index, because what essentially I have here is v to the 0, v to the first, etc., up to v to the n minus 1. So this is equal to the sum of v to the k for k ranging from 0 to capital N minus 1. And note that I also take the v outside of the expectation because v is deterministic. And what do I have now? I can use the geometric sum formula. And what I have inside here is then replaced by v to the capital N minus 1 divided by v minus 1. And I can also take the v minus 1 part outside. So I have v divided by v minus 1. And then I have the mean of v to the nth minus 1. What I can now note as well is that since expectation is linear, this is equal to the mean of v to the nth minus the mean of 1, which is just equal to 1. And the rest is actually basically, a lot of the rest is just basically computations on your part. So it kind of depends on what you how neat you want your answer to be. But we can start by plugging in the mean of v to the n because we just calculated that. That was given by p divided by 1 minus v multiplied by 1 minus p. So let's just try to plug that in for a second. So here I have p divided by 1 minus v to then multiplied by 1 minus p, and then minus 1. And if I chose to put that minus 1 into the onto a common denominator here, then what I would do is minus 1 plus v multiplied by 1 minus p, right? What else? Is this right? Yes, so what can we do now? Well, we can try to well, we can see that down below we have we have v minus 1 multiplied by this thing here. And then it could be nice if we could kind of find some v minus 1 up here. So let's just do a bit of improvising here. is there any v minus 1 that we can find up here? So let's try to say v minus 1. Well, we also have 1 minus p. It kind of looks like that v minus 1 multiplied by 1 minus p actually gives what we have up here. So let's just test that. We have v multiplied by 1 minus p. And then we have minus 1 multiplied by 1, which is minus 1. And then minus 1 multiplied by p, which is plus p. Whew, that was lucky. I thought that this wasn't going to work out for a bit. So this is actually, so actually I've just noticed that the numerator can be written as the product of these two things. And that's extremely nice, because then what I have is v multiplied by v minus 1 multiplied by 1 minus p. And then in the denominator, I have v minus 1 multiplied by 1 minus v multiplied by 1 minus p, like this. And these two go out. And then I have v multiplied by 1 minus p divided by 1 minus v multiplied by 1 minus p. And I don't think it can get that much more neat than that. So let's just stop it here.